Ginseng is the colloquial term for the root of the plant Panax ginseng, also known as Asian or Korean ginseng. It has primarily been used as a dietary supplement in the form of an extract, tea, or herbal medicine throughout Asia for centuries, creating a deep cultural significance. Ginseng's alleged health benefits are due to the family of active compounds present, known as ginsenosides. Ginsenosides are most concentrated in the roots, which are used for extraction. They are a class of triterpenoid saponins with the various chemical structures leading to distinct pharmacological effects such as improving stamina and immune support. Despite modern research indicating subtle effects on humans, ginseng is still often used in traditional medicine and as a supplement globally. We opted for high-pressure accelerated solvent extraction because it reduces energy and solvent requirements as well as extraction time required to achieve a similar yield to conventional methods. Accelerated solvent extraction works by exposing plant matter to solvents at high pressures and temperatures, which are elevated past their normal boiling points at atmospheric pressure, which increases solubility and reduces viscosity, enhancing mass transfer.
These are the main pieces of equipment that our team utilized to complete the experimental trials. The Thermo-Accelerated Solvent Extractor 350 was used to extract the ginsenosides from the ginseng root. The TurboVap LV was used to evaporate the solvent from the extractor. Our experimental results were then validated using HPLC. The ASE 350 operates at a pressure of 1500 psi. The parameters we were able to control with the extractor were temperature, solvent composition, and the static extraction time. The solvents we chose were ethanol and water. The team used 11 milliliter extraction cells to hold the ground-up ginseng powder along with diatomaceous earth. We started by weighing out the ginseng powder and diatomaceous earth at a ratio of 4:1. Each extraction cell had to be used with a filter on the bottom. We then loaded the extractor with our extraction cells and let the process complete. The extracts were then concentrated to dryness in the TurboVap LV with a water bath at 75 degrees Celsius and a constant flow of nitrogen gas. Upon drying, the extracts were reconstituted using pure methanol and filtered using a hydrophilic 0.45 micrometer PVDF filter. This was done to prepare the samples for validation in the high-performance liquid chromatography machine. To quantify the yield from each extraction trial, we used high-performance liquid chromatography under a water acetonitrile gradient. We used the ginsenoside RB1 as our standard because it is the most abundant in the root and it was within our budget. We built a calibration curve from that standard, ranging from 0.05 to 1 milligrams of RB1 per milliliter of methanol. We were able to quantify the amount of ginsenoside RB1 in our reconstituted extracts through identifying the characteristic peak around 39 minutes of retention time. The area under that peak could then be converted to concentration using the calibration curve, which subsequently could be used to calculate yield.
A box-Benkin response surface design is a structured way to model how multiple extraction variables interact, especially when the system has curvature. Rather than testing every extreme combination, it strategically samples mid-range points so we can estimate both interaction terms and quadratic effects in as few experiments as possible. For this study, the three factors that we varied were solvent composition, static extraction time, and extraction temperature. The box-Benkin layout lets us map the response surface efficiently while avoiding unsafe and unrealistic operating conditions at the corner of the design space. In our 11 experimental runs, we saw RB1 yield span from about 1.5 up to nearly 3 milligrams of RB1 ginsenoside per gram of dry feed. The clearest trend is that the mid-range temperature of 125 degrees Celsius consistently produced the highest yields, which signals a strong quadratic temperature effect. We also picked up interaction behavior, especially how ethanol percentage and static time shift the yield when the temperature is held at a mid-level, exactly the kind of patterns the box-Benkin design is built to reveal. When we look at the fitted response surface model, the qualitative trends line up clearly with what we saw in the raw data. Temperature shows the strongest curvature. The surface rises sharply into the mid-range and then drops off, which matches the large negative temperature squared term in the equation. Ethanol percentage also has a clear positive effect, but with diminishing returns at the high end, which is why the ethanol squared term pulls the surface over into a gentle plateau. Static time, on the other hand, barely shifts the surface at all. You can see that in the nearly flat contours along the time axis and in the very small coefficients in the model. Overall, these surfaces give us a qualitative map of the process. Temperature drives the peak, ethanol tunes the height of the peak, and static time plays a much smaller role. Even though our model shows a very high R-squared of 0.98, the apparent fit is misleading because we only had 1 degree of freedom for error. The model is essentially forced to fit the data we collected, which creates overfitting rather than true predictive power. You can see this in the adjusted R-squared, which is 0.8, and the fact that none of the individual terms are statistically significant, as every coefficient p-value is well above 0.05. This happens because of the incomplete design, and missing runs leave the model without enough information to estimate variability and curvature reliably. So while the surface looks smooth and the equation captures the qualitative trends, statistically, the model doesn't have enough power to generalize beyond the exact points that we tested. Even though our model isn't statistically powerful, the optimized conditions it produces are still physically reasonable. The solution it finds, around 62% ethanol, a short static time, and a mid-range temperature, aligns with the qualitative trends we saw in both the raw data and the response surfaces. Higher ethanol improves solubility up to a point. Shorter static times perform better at high ethanol levels, and the model consistently showed a yield peak in the mid-temperature region. Because these optimized conditions fall within our experimental design space, we're interpolating rather than extrapolating, which makes it a defensible first-pass estimate. So, while we wouldn't treat these values as final, they give us a grounded starting point for a follow-up experiment and process design.
Our industrial process operates in the semi-batch mode using two extraction vessels, one actively extracting while the other undergoes backflush cleaning. Dried ginseng is mechanically processed and subsequently contacted with the optimized solvent at 1500 psi for a 5-minute static hold. The slurry is then flushed through to a filter to separate solids from the solvent-rich liquid, which is throttled and flashed upon depressurization for a phase separation. The vapor is condensed and recycled, while the liquid fraction feeds a kettle reboiler that removes remaining solvent. The concentrated ginsenosides are then reconstituted to achieve a 4% product concentration.
Here is the industrial scale process flow diagram with the mass stream table and the utility table below. We selected equipment that would be sufficient for the utilities and flow rates that our process demands. Our industrial process consumes 362,300 kilograms of dried ginseng per year, which produces 93,150 kilograms of ginseng extract per year.
This is an outline of our capital and annual operating costs. The main takeaways from the graph on the left are our sales of roughly $4.19 million when selling ginsenoside extract at a standard market price of $31.81 per ounce. The sales revenue slightly outweighs the total production cost, giving a net earnings of $105,000. The graphs on the right outline the feedstock, equipment, and utility cost. As shown in the feedstock cost table, our raw ginseng is by far the largest expense in our process, with a wholesale buying price of $7.69 per kilogram. We expect to spend around $2.75 million a year on dried Pan-X ginseng. As for our utility cost, our plant will spend $241,000 to operate our equipment, and our equipment cost after factoring installation, piping, and labor is $2.4 million. This is our cash flow analysis table. It outlines how our project requires large upfront expenditures in the first 2 years from total depreciable capital and working capital during the construction stage of our ginseng plant. Starting in year 3, the project generates positive annual cash flow from operations, with our sales exceeding operating costs and producing steady net earnings. However, the cumulative present value remains negative through year 11 at about negative $0.18 million. This indicates that the project nearly breaks even, but does not fully make a return on investment at the end of the project's 10-year life cycle. For future work, the experiment should be repeated using the full set of trials so that the model can become more robust. Moreover, the optimized conditions should be validated to confirm that the selected operating point is reliable and reproducible. Access to a wider range of ginsenoside standards would enhance our ability to accurately measure concentration. Finally, the industrial process design could be developed further by defining details such as piping requirements and operational logistics more clearly through simulation.